How's it going, ladies and gentlemen? Mr. Donahue here. Starting a new unit about phases and phase changes. So solid, liquid, gas, and changing between those. So what are the different types of solids? Believe it or not, there are different types of solids, and we're going to talk about that today. We're also going to look at what happens when things go from a solid to a liquid and from a liquid to a gas and vice versa. So what's going on in terms of the molecules and energy? We're also going to talk about how much energy is needed for each of these changes. So if I'm going from solid to liquid, how much energy does that take? Or if I'm going from liquid to solid, how much energy is given off? We're going to be looking at that. So today's objectives with this video, I'm hoping that you guys are going to be able to describe the properties of different phases. So what makes solids different than liquids and liquids different than gases. Distinguish between the different types of solids, and you can do a little research and find out, apply this information to figure out, well, graphite and diamond are made up of exactly the same stuff, carbon. They're both just carbon, but how can they be so different? Graphite's great for pens because it's really, or pencils, because they're really soft and it'll leave marks all over the paper, whereas diamond, you're not going to use diamond for that. It's a lot harder. It's a 10 on that scale, ohm scale. So solid, start there. Let's think about this. This is kind of what a solid looks like. You may look at a solid and think it's not moving because you're looking at your desk and you're like, my desk is not moving. But if you were to, shrink down to the size of molecules and look at it, you would see that those particles are actually vibrating in place. They're kind of rigid relative to each other. They're locked into place, but they are moving. They're vibrating. They can't move past each other because they're locked into place. So would that be high, medium, or low attraction, you think, for solids? That's going to be high. They're really attracted to each other. They're locked into place in between each other. So how do they move? They move just like this. They're freaking out, right? They're on edge. They're shaking. They're, I'm freaking out, man. That's how they move. Liquids, slightly different. They can move past each other. They can move around, and you got to forgive some of those water molecules or whatever they are escaping. The liquids can flow past each other, which you see down here, and then you also see up here some of them becoming gases. Right? We'll get more into that later in the unit, but you always give off some gas. You have a liquid, some of it's going to evaporate at the surface and become a gas. So high, medium, or low attraction between these molecules. Give you a hint. It rhymes with medium. Exactly. It's medium. Good job. How do they move? They move like this. They can flow is a good word. They flow past each other. And here's a cool video on proof that they are attracted to each other. All right, this is on YouTube. You can watch it on this link, but I'll put it in this video.
Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Time to line. Houston, requesting EMU check over. Okay, it's quite dark here in the shed. A little hard for me to see that I have good footing. I'll work my way over into the sunlight here without looking directly into the sun.
Alright, so gases are different. Right, they're moving all around. I got this box here. The particles represent gas particles, and you can see they're moving around in straight lines till they hit something. So look at how attracted are they to each other. Well, it looks like they don't really care about each other. They'll bounce off each other and just keep going. So that's a low amount of attraction between those particles. How do they move? They move in straight lines. Right? The faster you get it, or the hotter you get it, if you were to put this on fire, they would move faster and faster because you give them more energy to move around. So we're going to get into types of solids, but before we do that, I want you guys to think about what electricity is, because we're going to talk about whether or not these solids conduct electricity. And the simple question is, well, what is electricity? And the simple answer is moving charges. Whenever you have charges that are moving, you got electricity. So in a battery here, here's a voltaic cell. Got some zinc. We got a compound that has zinc in it. We got copper and a compound that has copper in it. Well, what's happening here is zinc is losing the electrons to copper. So the copper is gaining electrons, and we got electrons moving through a wire. So you got to remember that electrons are negative and they're moving. So we have electricity. That electricity can be used to power our mobile devices. Right? You got a phone or something, whatever you're watching this on has electrons flowing through, powering it. Right? So that's all electricity is. So I want you to think about that when we're talking about whether or not these things conduct. So let's first talk about metallic solids, because they're in the wires and stuff that are conducting the electrons and powering your devices. So the question is, what's holding these metal atoms together? Why do they stick together? Well, there's this thing that they call, cleverly, metallic bonding. So all these metal atoms share their valence electrons with each other. It's kind of like socialism. Everybody's sharing everything. This electron is free to move around and go wherever it wants. It can go anywhere. It looks like an electron it's an electron sea, kind of. All those electrons are moving all around. They're free to go about, and all of those atoms share all of the electrons. So, question: is it soluble in water? Are metals soluble in water? No, thankfully, because could you picture, driving down the road in your car and be like, oh no, it's raining, and then, well, what would happen to your car if it just, was soluble in water? It would dissolve, and you would just be sitting in a puddle and wouldn't get anywhere. Conductivity. Metals will conduct in all phases. Now remember, conductive means it can carry electricity. So if we're looking at a metallic solid, can there be moving charges? Absolutely. Those electrons are free to go wherever they want. So this is going to conduct electricity because we can have charge flow from one end to the other because we have mobile charges. We have mobile charges. So it'll conduct. And the melting point of these things vary. So it could be relatively high, it could be relatively low. It all really depends on what the metal is. So melting point varies, depends on what metal. We also have ionic solids. So the first question is, well, what's holding it together? Well, a friendly reminder that ionic solids have ions. So for example, the red spheres might be positive. I should choose a different ink color. I'm totally going to do that. Green. So these spheres are representing different ions. So we got positive ions and negative ions. And what do we know about opposite charges? We know that they attract to each other. We call this the electrostatic attraction. Electro, because it has to do with the charge. Static, because the charge isn't changing, it stays positive and the other one stays negative. And attraction, because they're attracted to each other. So if you were to look at an ionic solid, you would see a kind of a regular pattern. You would see positives pairing up with negatives and negatives pairing up with positives because opposites attract, and that's what's holding them together. It's a pretty strong attraction between those ions. Solubility in water, yeah, these things are salts, so they dissolve in water with some exceptions. If you remember table F, you can look and see what things won't dissolve, but generally ionic solids are soluble. Conductivity, well, we have charges when it's a solid, right? You look right at this thing and they're all different charges, but the issue is right now they're not mobile. They're not free to move around. They're locked into place when they're a solid. But if you were to melt this into a liquid, well, now those charges can move around. They'd be free to go, this way and that way, and then they would conduct. Same thing if it was a gas. And also, if you dissolve these in water, you're breaking these things apart. So now they're separate ions surrounded by water that are free to move around. So they're conductive as a liquid, as a gas, or when they're dissolved in water. And these things generally have a high melting point because this attraction between opposite charges is really strong. So it takes a lot of energy to break them apart. And the last solid we're going to talk about is a molecular, or I'm sorry, the third one that we're going to talk about is molecular solid. And the key thing here is they are molecules, right? So we have molecules in a solid crystal. So how's that working? What's holding them together? Well, you got to remember it's the intermolecular attractive forces, which I abbreviate IMAFs. So for like water, if it was water, you have the hydrogen bonding between them, which is going to hold the molecules in place. For this example, the dotted lines are showing the attractive forces. They're not covalently bonded, they're just kind of attracted to each other, whether it be hydrogen bonding, dipole dipole, or the London dispersion forces. They're holding them in place. Solubility, yeah, they can be soluble. You know, there are exceptions. There are molecular solids that won't dissolve, and then there's molecular solids that will. But we generally say they're soluble. Conductivity, they are not conductive at all because there are no charges at all. All right, so if there's no charges, there's no mobile charges, which means they can't conduct electricity. Now, the melting point of these things also vary. Some things melt really, really low. Some things melt at pretty high temperatures. Like dry ice would be a molecular solid because it's made up of molecules of carbon dioxide, but it has a pretty low melting point. Whereas, I don't know, wax has a relatively higher melting point, so it varies. It depends on the solid. And everybody's favorite, the network solids. Question is, what holds network solids together? Well, if you were again to shrink down to the size of the molecule, you would see that every atom in the solid is covalently bonded to each other. So it's forming a network, right, of all these connections between these atoms. So the solubility, well, no. Water's not going to break these apart because they're actual covalent bonds. It's not going to be enough to break them, so they're not soluble. Are they conductive? No, because there's no mobile charges. And the melting point is really high because you're not separating molecules, you're breaking bonds. And that takes a lot more energy than it does to just separate a molecule. So here's one image, and then here's a 3D rotating image of molecular solid. You can see that everything is bonded to each other. It's one big molecule, kind of. It's a network. So here's a question that you guys are going to answer via a lab. You have two unknown solids. You know they're either molecular or ionic solids. That much I'll give you. But you got to figure out what could you do to determine which one's ionic and which one is molecular. How are they different? How are they the same? What will be helpful? All right. I will see you in class. Bring some questions. I look forward to answering them.